How's everybody doing? Just setting a few things up here. We're pretty much ready to go. Yeah, assembly line for sure. All right. Yeah, so Humpty Dumpty suggested that we look at this Babuk locker sample or ransomware sample. The interesting thing about Babuk is the Babuk source code leaked quite a while ago. Because of that, there's actually like a ton of variants of this in the wild. And I think this is one of those variants. So, but yeah, I thought it'd be a good sample to look at just because we have a lot of different functionality that is pretty common to see in ransomware, especially ransomware written in C. And then there's also some newer techniques that I haven't talked about before. So I thought it'd be good to look at. Let's see, Babuk, is it on here? Babuk builder. Is it just the builder I'm thinking of, or the source code actually leaked? I can't remember. Oh, nice. Thanks. So yeah, here's the source code. Okay, so it has all the variants. So it's because it's Babuk. I'm going to add this to my notes here. For the sample that we're going to be looking at today, in case you all want to grab it, here's the triage link. Let me copy that source code path into this as well. But yeah, the nice thing about when the source code leaks is you can compile it yourself if you really want, but you can also just glance at what the ransomware is doing. So if you get stuck on like a piece of the code when you're attempting to disassemble or decompile it, you could just literally look at the source code. So it's a really good learning opportunity when these things happen. I opened this up in IDA already. So again, we're going to start out at the main function here, and then we're going to work our way through the samples. So this is a pretty standard static analysis approach where we start at the start function, which happens to be the address of entry point within the portable executable. And then we kind of just recursively work our way through the functions in order to assess exactly what they're doing. So fortunately, again, this is a good learning opportunity because this particular sample doesn't have a ton of obfuscation. So we can work through most of this statically without any dynamic analysis, really. I don't really think I'll need it depending on whether or not there's difficult parts to get through, but we'll see as we go. So, okay, so I'm going to put these side by side just to make sure that this isn't actually a empty function. And I'm going to sync these, but I'll move this over because I know the chat covers it. But let me synchronize this with the IDA view, and let me go back to that function. Okay, so this function just moves ESP into EBP and then pops it. So it pushes it, moves ESP into EBP. Okay, so it's just literally getting the old EBP address and then moving ESP into EBP. So that's all this function's doing. So just set up stack. But it's also setting up the stack here, so I don't really know what the point of that call is. If somebody does, let me know. Good watching, good working and listening, watching, nice. Yeah, we're just working on this Babuk sample. That looks pretty straightforward in IDA today. Okay, and then this gets the process heap and then returns that in EAX. So, and let's take a look at hprov. So this is a crypto provider that is acquired using acquire context. So we looked at something similar last week, but if I pull up the documentation here, it's W, but we don't have to worry about whether it's ASCII or wide at this point in time. But yeah, again, this is going to provide a pointer to a handle of a crypto service provider, I believe is what CSP stands for. Let's see. Yeah, cryptographic service provider rather. And then we have the container pointer, the provider, and then the provider type. So usually when you have this crypto container being set up, we basically want to ensure that the correct type is identified, and then if there's any flags associated, etc. So if we look down here, I can just get the type by going to this argument. So in IDA, if you hover over the arguments, then you can see that the provider type is the fourth argument there. So if I go to this is the provider type, and if I hit M, then I can look for this enum. Is this not loaded? It might be an ord. No, those are for the flags. So we actually want these provider types. That's why it's not coming up. So it's prov underscore, not crypt underscore. And again, this is provider RSA AES. So this is commonly used for, I believe, using the Diffie-Hellman key exchange in order to acquire an AES key at runtime and then use that to encrypt files. But we will see if that's actually what this provider is being used for. And again, that's what is being returned in this argument here. So we can just call this get encrypt provider. And then we have the command line arguments that are acquired. We have a pointer to those. I believe that's what, or well, PNM arguments gives us the number of arguments. And then we actually have the command line W. Let's just double check the docs on this. I just want to make sure that I'm not spewing nonsense. So if we look at command line to argw, then we can see that it's a pointer to a null terminated Unicode string that contains the full command line. So if this parameter is empty, blah, 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 returns the path of the current executable. So that's also good to know if that's being used here for that. And then we also have the number of arguments, or the number of array elements returned rather. Deluxe, is there a reason you started with static analysis? Curious, since I hear that dynamic analysis usually gets you the quick wins. Yeah, so I could probably back up a little bit to a non-static analysis workflow if you're all interested. But the first thing I did here, I ran this in my assembly line instance. So this is a really cool open source project from the Canadian Center for Cybersecurity, assembly line 4. So I'm just going to link that. And this will do a whole bunch of static analysis for you. I have like Yara rules that run against samples, etc. So that's what I'm using here. And then, hey, Demify, how's it going? And then we also have that triage run that I mentioned earlier. So I'm not doing any manual dynamic analysis right now, just because this is pretty easy to reverse, as I mentioned. But usually if I don't understand a particular piece of code or don't understand what an algorithm is doing, etc., then I'll usually perform some dynamic analysis alongside my static analysis. So this is that triage run that I mentioned earlier. And it's identified this as Babuk. And then what's kind of cool is it provides like a timeline. So the RAS was first seen in 2021, called Vassalocker, and then just provides some TTPs. So the fact that deletes shadow copies, renames a bunch of files, etc. So it identified it as ransomware based on that, checks the computer location settings, enumerates connected drives. So these are all kind of very common things that you would see in a sandbox, but this is like a form of dynamic analysis. And if I go to like one of these Windows runs, then you can see that this has a whole bunch of stuff. So Babuk will just delete shadow copies using, we're going to see this in the code in IDA, but it deletes shadow copies using this vssadmin, deletes shadows all quiet to do that. And then I don't know what it's using the VSSVC service for, but, or whatever this binary does, I actually can't remember. Oh, it's for the volume shadow copy stuff. So there might be additional volume shadow copy stuff that it's doing via a different interface rather than just command line, or this process might get spawned whenever vssadmin is called. I can't remember. Is it a good idea or efficient to learn Golang/Rust syntax to learn reverse engineering them? Yeah, absolutely. Captain Nobi. Definitely a good idea to learn both their syntax and learn how to write them in order to reverse engineer them. I've been doing some Rust work just in order to get a better handle of how a lot of the Rust syntax looks and how it's manipulated at runtime, and then even how the compiler works, because there's like a lot of LLVM artifacts that are embedded within the final binary for Rust. So I've been trying to do that. And then I've written some Golang as well, so that helps a lot. And then just understanding, like, for example, Golang is statically linked, so it embeds a whole bunch of information. Same with a lot of Rust artifacts as well. It's creating huge binaries with a huge amount of functions, etc. So they're kind of similar in that way. I think conceptually that's true of any of those higher level languages. Yeah, exactly. Permanent. That's exactly right. So, okay, cool. So let's get back to this after my tangent. Okay, so we have the number of arguments. It looks like it's just looking for the debug flag here. So we have process arguments, which was this from the binary? Okay, yeah, so sorry, I let Lumina run so that we're gonna cheat a little bit here because Lumina ran in the background when I opened this binary. So this process arguments function is already renamed, but we'll take it for free. But if we look at kind of what this function is doing, It's looking for these dash and equals artifacts, not artifacts, dash and equals characters. And then it's just checking them and looping through those character sets. And it looks like it's incrementing this particular index if they're found. So it looks like it's just essentially processing those arguments, and then it is setting the pointer to those. Not equal to 6 is equal to incremented. Yeah, so I think it's just providing the offset of the string to be checked for within the arguments string. And then it's essentially entering a second while loop once it hits a dash, meaning the switch statement. Switch statement as in like dash argument, so dash debug would be what I'm alluding to. So that's basically what this is doing. So this is going to be the argument. And is this looking for anything outside of debug in two other places? So shares and paths. So what's kind of nice about having this marked up already, so I'm just going to call it MW process arguments. We know that the ransomware takes the debug switch, the shares, and the path switch. So like these are all really important things that we need to make note of. So shares, arg, pass arg, and then debug arg. And I'm assuming that if the debug argument is provided, then this is probably going to initialize some debugging routine. Yeah, it's creating a file. So this is going to be create debug file. And then this is the debug argument. So it's probably taking a debug file name, I would presume. And then this is going to be debugging enabled. So just to kind of explain how I got there. Sorry, lots of chat that I should probably address. What's the difference? Okay, hold on, let's see here. Compiled to binary, not C. Python compiled to C. Yeah, I think in most instances, compiled Python is effectively shipping the interpreter within like a package, and then that. But I know it does get compiled to Python bitcode and whatever. So I don't know, that's kind of a whole other discussion. What's the difference? Lucisoft, I'm not sure what you mean, but maybe that was alluding to the above. It's always the best way to gain a good understanding quickly. I usually write some code in the language of a sample. I reverse it to get more comfortable with how the code looks. Yeah, for sure, Lopsec. I'm sure you had to struggle learning some Objective-C because it's really weird. Or I think it's weird. Bad codes, they're different sample from last time. Yeah, sorry, bad code. This is a Babuk sample. Here, I'll give the triage run and see. I don't know if you guys can download that actually without a triage account, but I'll link that. But yeah, this is a ransomware called Babuk, which is, as I mentioned earlier, the source code leaked. So that's that. And then I just asked AI to write some code. I could compile and reverse that, but should probably just learn how to write it myself. Yeah, that's a good approach, Captain Nobi. But knowing how to write it yourself is obviously a step up, just because then you're able to understand, like, this is exactly what I need to do within the syntax in order to be able to write a program effectively. And this is how I import libraries, and this is how I pass arguments, and this is how I pass by reference and pass by value and whatever. So let's continue looking at our functionality here. So as I mentioned earlier, so if a debug argument is provided, I think this is a debug file name. Let's see, debug file name, CNAME. Okay, we'll look at that in 2 seconds here, because yeah, I think it's just writing this is a debug log, and then this is freeing that. Can't find. Okay, we'll look at that later on. It looks like that's just the writing to the debug file, and then this actually might be the debug log handle. So it's going to write the LP file name. No, so I was right. It's returning the handle here, but it's not showing in the decompilation. So I realize you guys were probably not able to see that because of chat. Let's see, EAX. Is EAX used later on? Process number of arguments. That's okay. We can continue looking at that later. And then if we can probably move this over for now. Okay, so let's take a look at this function that's called for main after the debug log is set up. We have get tick count is called. Then we have 30,000 milliseconds probably. that are used somewhere. This might be anti-analysis. Maybe not. Let's see where else this is used. Current state. Oh, I think it's used to set up this service and check how long it's been alive for maybe. But let's go through this properly rather than me guessing. So let's just call this alive time or something. So this is opening the Service Control Manager. So on Microsoft Windows, for those of you who are not aware, you have this concept of services. This is kind of similar to daemons on Linux, but these are often used for running various background services that are utilized by the operating system. And ransomware will often enumerate these services in order to see if there's services that it needs to kill in order to kill handles to files that it wants to encrypt. So let's see what, okay, all this is heat free. Yeah, so just to kind of illustrate this further, let's see where this is being called. This should be called elsewhere, but this is very common. So in ransomware. So enum dependent services A. So this will actually recursively enumerate a given service in order to, okay, so we have an index here. So if I double click on this LP service name variable here, we will see in the left-hand side here, this is actually a list of pointers. So this is essentially what I was talking about earlier, where the ransomware will look for certain services that are running in order to terminate them, in order to encrypt the files that they might have open handles to. So a lot of ransomware will have these lists that are hard-coded within the ransomware that are common applications or services that might have handles open to files that they want to encrypt, essentially. So these are often things like applications that might be used for productivity or backup services, or what else do we have in here? Things like QuickBooks, so like accounting software, stuff like that. So these services would have Sophos, so like even antivirus, I guess. Veeam, so this is like backup stuff. So this is basically services that could be related to things that they would want to encrypt or stuff like that. So if I go back here to the decompilation, the enum dependent services A function that I was talking about earlier is basically going to recursively enumerate a given service name for its dependents. So there's like a hierarchical concept in Microsoft Windows services where it has not only like a parent service, but also the services that are dependent upon that service. So you can think of like, say you have a database software that's dependent on a parent service to be running before it can run its children. That's basically the reasoning for that. And sometimes you won't be able to kill its parent unless you kill its children. So that's basically what it's doing here. So let's see. So if we Google get last error, yeah, I should have the error code loaded already. So weird, because usually I can search the existing ones. Error more data. Is that actually what it's looking for? Probably not, but I would assume that if there's an error associated with enumerating the service, that's what it's checking for. But okay, so let's see what structs that it's identified automatically, and then if we need to change anything. So in this service enumeration functionality, it's basically copying a given service index in that list that I showed you earlier into this LP service name pointer. And then it's passing that to open service A, which basically opens the SC object. I can't remember exactly what this stands for, but basically it's a open handle to the service. And then control service is used to manipulate that service. So if I pull that up, oh, cool. Thanks, Orphis. Okay, access denied. I would presume it's, oh yeah, no, it is error more data. So the buffer for the pointer LP services is not large enough. So I guess it just needs to allocate more memory to read the list of dependent services, I presume. Cool, thanks for that. I guess in IDA, if the value doesn't exist in any of its non-loaded types, then it probably doesn't prompt me for being able to search those as well, or load those additional ones. So I assume that's what's happening there. Okay, so as I was saying, control service is basically used to manipulate a given service with a handle once it's opened. So if I use control service, or sorry, Google control service, then it sends a control code to a service. And then if we look up the control code that's used in this instance, which is 1, it's service control stop. So if I hit the M key in order to pull up, okay, see, this is what I was talking about earlier, like add standard enum is what I was looking for. Service control stop, sorry. Okay, so that's basically just going to stop a service from running, and then it just ensures that it basically uses a loop after that and will query the status in order to assess whether or not the service has actually been stopped. And then, so this is where the get to count value is used from the beginning. So it's subtracting that from the current get to count value. And it looks like it just tries to stop the service, or it basically waits for the service to stop for like 30 seconds. 30,000 milliseconds in seconds is 30 seconds, I believe. Hey, Goovescoof, how's it going? So here we can basically just say query for 30 seconds or until service is stopped. So I try and just add the higher level functionality as I go. And then the buffer here for control service is the LP service status buffer, which it's a pointer to that. So if the service status structure probably has a exit code or something that it's checking for. So yeah, so the DW current state, which corresponds to one of these. So, and then 1 corresponds to service stopped, unsurprisingly. So we could just say service stopped here. And then I think that's basically it. Service, yeah, it's the buffer size, so we don't have to worry about that. So yeah, again, just kind of iterates over a list of services and then stops them. So MW terminate service. And then here we have a very similar piece of functionality. Again, this isn't really like hard reverse engineering because it's largely marked up for us by IDA, which is nice. But we can still kind of assess the functionality and establish what's missing and et cetera, et cetera. Hey, Natural Walker. No, this is actually an old Intel Mac. So that's why I can run virtual machines on this that can actually run Intel x86. I do have an ARM Mac that I use full emulation for running a Windows operating system, but it's quite slow. Okay, so let's take a look at this function. So again, on Microsoft Windows, you have processes similar to other operating systems, where here we're taking a snapshot of all of the processes running in memory. So this API create tool help 32 snapshot will do that for us. And if I look up that, then there's this DW flags parameter, and it's this th32cs snap all, I believe. Unless it doesn't actually need to snapshot everything. It might just be snap process. Let's check. It's F. It's not in here. Yeah, snap all. So it'll take a snapshot, which returns a handle to that. And then it passes it to this process 32 first W. And this function will essentially enumerate every single process in memory. And then if we, again, hover over this to see what is being passed to process 32 next W, we can see that there is an LP process entry 32W structure that's being passed as the second argument here. So that's what this is. And again, helpfully IDA has done this for us, so it's not very hard, or mark this up for us, so it's not very hard. But then it basically just compares the exe file name to a string here. So if I double click on this on the left-hand side, we can see that this corresponds to, unsurprisingly, a big list of processes that, again, they want to terminate prior to encrypting files just to remove any potential for handles being open to those files. So in this example, you have like MS Access and MS Pub and OneNote and Outlook and PowerPoint and Steam. So they want to encrypt and these are pointers to strings, I should mention. So if I double click on one of those, then these are UTF-16 LE strings. And then We have things like email clients and Notepad and SQDB core service, which is probably related to their SQL database stuff. And then agent service, I think this might be AV related. But yeah, basically they're just trying to kill any processes that might have open handles to stuff they want to encrypt. Come on, leave my games alone. Yeah, exactly. Okay. I've heard that not everything works with the new Macs when using the debugger. Thanks. Yeah, no problem. And thanks for YouTube replay. Yeah, no problem. Thanks for hanging out, Natural Walker. Okay, so let's take a look. How do we get into the service side here? I want to go back to where we just were, which is here. And then basically if it finds one of those names by iterating through the for loop. So here we can see, okay, there's obviously 31 entries within that list of processes. Then it opens a handle to the process. So if we look at the arguments here, the desired access that it wants for a process. So if I just Google open process again, we can see this corresponds to process access rights. And then I don't think it's any of these. Am I looking at the wrong argument? Process access all. Anyways, it's probably, oh, it's process terminate. Yeah, okay. So if we do process terminate, then it basically opens the process with the termination permissions and then uses terminate process to kill it. And then this is just the setting up the exit code for that. I don't know why it's 9, but maybe there's reasoning behind that. So let's just call this MW terminate process. And then let's go back here and let's continue down our list of functions. Again, pretty straightforward just because the decompilation is really clean, but this is still a good learning sample. And then let's open this. And by open, I mean navigate to that function. So here's just doing some dynamic function resolution. So this is what's commonly referred to as runtime or runtime function resolution rather than load time. So this is often used by malware just to have functions that it needs to execute that it doesn't want to keep in the import address table, or doesn't want to be set into the import address table from its import directory once it's loaded. But in this case, I think this is just like 64-bit compatibility stuff. And then, yeah, it's just using this for executing shell execute. So not entirely sure why this FS redirection stuff needs to be used, but I think it's just for the 64-bit compatibility. And then they're just calling VSS admin delete shadow copies. So this is the command line argument that we saw, or the command line arguments that we saw from that hatching triage run. What's the difference between this version? That's kind of what I'm trying to figure out hexamine. There might actually not be any, but for some reason, oh, okay, this is just getting, so is what 64 process. Yeah, so I'm just trying to figure out if there's actually any differences. That's a good question. Because for some reason the sample was called something weird. I can't remember if it was assembly line that was weird or something else. But yeah, we'll take a look in a second here. Like this is calling it, so this is just like public Yara stuff that I have, but this is Astra Locker. But I think that might have been another name for Babuk. Let's see. Did they refer this as Babuk? Astra Locker 2.0. Okay, so yeah, this might be the Astra Locker variant of Babuk. So if that answers your question. But that's just based on a Yara rule. So let's see if we can actually find any indications of that in the code. Does antivirus walk the IATs? Not usually, Tumpus. Well, okay, they do, but they'll often, like, you can use a whole bunch of different techniques like machine learning and even just writing like hard-coded signatures, but there's a whole bunch of things that you can do with the import table that they'll typically try to avoid. Because if you can see that a portable executable has certain types of imports, then you can kind of infer that it might try and do certain types of functionality. So that's why malware authors will often leave functions out of the import table that might lead to antivirus thinking that it could be malware, if that makes sense. So then they'll resolve it at runtime. But AV does walk the import table for processes running in memory, and then it adds hooks usually. But usually it's done in the kernel because user-line hooks aren't the greatest because they can just be modified or removed. So hopefully that answers your question. Okay, so yeah, so for those of you who are not aware, again, not familiar with Windows, they have these concepts called, this concept called shadow copies. And basically this just keeps a second copy of a file on disk in case it gets corrupted, or in case for whatever reason the original file gets removed or whatever. So this is often used by Windows users to restore those files. So deleting these shadow copies using this VSS admin tool will prevent the recovery of that file. So this is like basically anti-recovery stuff. So I'll call it that. sh empty recycling bin A, as you can guess from the name, this is basically just emptying the recycling bin on a given machine. So this is pretty straightforward stuff, where it has the handle of the parent window. This is probably null. So the only argument is actually providing this not null is the flags, which sherb, I don't know. Okay, so it's probably setting no sound or something. Let's see. I don't know if we have those types loaded. I need to have like a open instance of, but yeah, basically this has this empties the recycling bin in case they have any files there that could be used to restore the system. And then the next thing it does is it will acquire the number of processes. So the way it does this is it calls this get system info. And then if I pull up the docs for that, then we can see here that this is going to be provided a LP system info structure. And this is often used to query various types of system information. So if I go to this struct, it has like the process architecture, what are actually useful things here? Usually it's just for like the number of processors is what I usually see. I don't really see it being used for a whole lot else, to be honest, or the processor architecture. But in this case, it's basically being used to acquire the DW number of processors, and then it multiplies that by 4. I believe that's just to get the number of cores, or an estimated number of cores. I think that's why it's doing that. Binja, where I can put question marks in variable names. Let's see what this unc pointer is for. Not really obvious. It's timesing that by 24 here. So create semaphore, critical section. So I'm just going to make this a struct LP critical section. So if I just make this I'll just make it a pointer. Okay, so this is the recursion count for whatever reason. This might be incorrect, but that's okay. So I think semaphores are used for threading, if I remember correctly. Unnamed semaphore object. Let's see. Probably don't have to worry about this too much. I hate these AI responses, but yeah, it's used for synchronization primitives. And then is that going to be in that? So this is going to be the critical section. Okay, so we don't really have to worry about this too much as like malware analysts, but still good to mark up so that there's so that we don't, like, say we see this variable elsewhere and then we're not quite sure what it's used for. We know that, okay, it was using that semaphore operation. So okay, so this is the number of handles. Okay, this is doing a memset, and the reason I know that is just because it's doing the number of characters here, and then it just initializes every index within this array to this value, which is the memset value. So okay, so it's initializing all these LP handles, or this LP handles value to 0, and then it's setting this one to, I don't know, and then it's starting a thread. So oh, sorry, I see the chat still going. I guess 7 means all that. Yeah, I think you're right. Another point for binge locks. Like, yeah, I've just been doing, like, the vast majority of my content has been binja. So okay, so here basically they are getting the number of shares, and then they are looking for comma separated values within those shares, and then they're incrementing the number of shares by 1 from the arguments, the process arguments, and then they're copying these over. So this will be shares. I'm going to go back to what that thread was created for earlier. That's probably the main encryption functionality. I just want to finish the rest of this main function first. Okay, and then it's doing the same thing with args. So num paths, and then it's doing, okay, and then it's looking for hard-coded drives, it looks like. Any questions? Pretty straightforward so far. Okay, so let's take a look at this threading functionality before we look at the networking stuff. So this is going to be, I usually just mark that up a little bit differently. So again, see like the critical section that we marked up earlier is used here. So that's why it was good that we marked it up before. And then wait for single object. Again, this is threading related. So I'll just change that to wait for thread because it's waiting for the semaphore. And then, okay, so still waiting or something. Still waiting. Okay, and then we have, let's see here. Okay, cool. So this is the ransom note stuff. So for those of you who are not super familiar with ransomware, so they'll write a note to usually all the directories that files are encrypted in, and then it'll basically give them instructions on how to get your files back in some way, shape, or form. So it looks like in this case, they're telling you to join some talks chat in order to get your files back, which is common. And then let's see. So yeah, this is our debugging stuff. So we start from the top here. This is going to be the file name, and then the access to that is going to be our DW shared access, desired access rather. And so it's probably just going to be like generic read write, generic write. And then it's going to basically just get a handle to that. This is the length of the ransom note. And then it's just writing to that file. So pretty straightforward. And then it will basically, it looks like it's recursively enumerating the file system from a starting directory using this // and then it'll basically enumerate all the files using this find first file function. Let's see. So if the debugging is enabled, looks like it's outputting that each file that is enumerated, and then find first file W creates this find file data structure. And this is used for, let's see here, they're accessing, so all I did here was I highlighted this and hit X to get the cross references to that variable. But basically this is looking for file attributes, the file name, and then what else? And then it's comparing them to specific extensions. So usually ransomware won't want to encrypt certain file types because it can lead to like system instability and stuff like that. So in this instance, they're just checking for exe and DLL. So if I go down here, so let's see, string length, wide char, the code pages. So this is going to be the type of wide character set maybe. And then okay, so this is the multi-byte string. And then it's getting the length. And then, oh, this is just saying, so this is when it can't get a handle. So it's casting the handle to -1, which is kind of funny. But yeah, this is when a handle can't get, so this is gonna be write debug. So when it can't get a handle to the file, then it basically says can't find first file W. And then let's see what else. It's just writing this again, the same file. And then let's see what else does that. So yeah, it checks for these extensions again because it doesn't want to encrypt these files. So I assume it's probably going to append .babuk to every single encrypted file. And then this is more threading stuff. I assume it's wanting to create a semaphore in order to write the ransom note. Okay, so let's set the file attributes. Which file is this? Is this all global? No, this is an argument. Oh yeah, okay. So file to encrypt. And then, what the hell? Didn't I just rename that? Oh wait, sorry. I didn't mean to change the function name. Inc file, there we go. Okay, and then set file attribute to AD, which I don't know what this is gonna be, but it's probably related to file access. We could probably look up file attributes normal probably. And then it's getting the string length of the file. and then it allocates the size. So this is just gonna be the file name, I think. It's probably converting it to wide again, right? Oh, it's just allocating the size plus the name, or plus the extension. So this is gonna be the file name plus extension, and then it moves the file. So another thing that you'll often see is some ransomware will like encrypt in place, which is basically what this is doing, but others will actually delete the original file and then, or sorry, encrypt the file, but like write it to a new file and then delete that file. But usually, sometimes that file can be recovered using forensics. So the thing that other ransomware authors do will do this encrypt in place thing, which basically prevents that, which is what they're doing here. And okay, so this is that crypto provider that was initialized earlier. So that's that global that we were looking at, the RSA-AES crypto provider thing. And then the reason they're actually using that is to use CryptGen random, which is a securely random, pseudo-random number generator that's from the Microsoft Windows API. And they're getting a 32-byte key. So this is going to be the crypt key. And then not entirely sure why they're setting, or they're ANDing the first byte or these operations. But again, we kind of cheated because I used Lumina when I started this, and that gave us that this is curve 25519 Donna. So does this not have, oh, that's the stack. So let's see where this is used. But basically, my public key, I think this got written up because of Lumina. But basically the ransomware makes use of curve 25519 asymmetric cryptography, which basically uses the curve 25519 public key in order to encrypt a generated symmetric key. So in this instance, this is like a 32-byte key that was generated using CryptGen random, and then that's being encrypted and probably written to this. I don't know what the base point is. And then cipher setup, again, kind of cheated. Probably should have disabled Lumina, but that's okay. There's cipher setup stages for this key and initialization vector. So let's call this, and if we look at HC128, this is a particular type of symmetric encryption. So HC128 basically takes a key and an initialization vector. Is it a stream cipher? Yeah, it's a stream cipher. So it's kind of similar to RC4 and Cha-Cha and other stream ciphers that are often used by ransomware. So, okay, so that's kind of the key setup phase. If we really wanted to find this ourselves, we probably would have either used, so we go back to my assembly line run, it also runs Kappa. So I could have looked at the Kappa output. Let's see. Oh, my session got killed. Okay, so if we look at the output here, then we can see Kappa. And then I just wanted to see if there was any HC128 stuff. These are kind of high level, so maybe not. Let's see capabilities. Yeah, cool. So yeah, so Kappa like could have identified the HC128 for us. And then potentially, I don't know what offset this is because I kind of want to change this assembly line service to give the actual offsets within the binary or the virtual address. But yeah, probably could have determined that was HC128 using that. And then they also identified the curve 25519 stuff. So that's probably how I would have done it, is used Kappa, just because it's kind of hard to like memorize all of these constants and things that are used, especially when like this cipher setup is kind of esoteric, right? Like there's just these random offsets and things that are used. There's not really a whole lot of constants. Like this might have been more obvious, but it's still like crazy cryptography stuff. Okay, so then again, cheating. Let's see what kind of checksum this is though. This might be a custom checksum algorithm. Yeah, it might be a custom checksum algorithm. But usually they'll want to verify the file integrity when they're decrypting them. So looks like this might be a 64-byte checksum, or that's actually being used for the key. Yeah, it might be checksumming the key to be used in the encryption operations. Okay, so there's some file size logic here. So also very common in ransomware is they will, like, say you have a file that's like a gig. You don't really want to encrypt the entire file because it'll take forever. So usually they'll have these like file size manipulation algorithms in order to only read portions of the file. So that's what they're doing here. So the quad part of the file size is acquired from get file size extended. So get file size X. And then the integer of that will basically be used to determine the file size. I think this is in bytes. So this would be what, like 2 gigs bytes to 20 megs. If that's what get file size W returns, let me make sure. Okay, let's check that API. So if we look at this, the LP file size is provided, and then it's a large integer structure. So this is like what Windows had to do to get by on only having 32-bit architectures for a while, is they had to use these like crazy union types and stuff. But the high part will probably be I think this is literally just the size. So I think that's right, it's probably 20 megs. And then, so if the file is 20 megs, then it goes down this branch. Let's see here. And if it's less than this, then it will encrypt the entire file, it looks like. It's actually accessing the load part of that large integer. And then this is just the HC128 stream encrypt, I think. And then it writes those to the file. And if it's larger than that, it looks like it only encrypts the first 100 hex 100,000 bytes. If it's not less than, if it is not less than hex 500,000 bytes, then it only encrypts this many. And then let's see here. Otherwise, yeah, same thing. So not like crazy important, but say you were like trying to recover files that were encrypted by this ransomware or something, it's good to know exactly what's going on with the file encryption. Okay, so the restart manager, this is very common as well in Microsoft Windows ransomware, is Windows has this concept called the restart manager that's actually used to terminate processes with open files to them when the system is being restarted. So that's why it's called the restart manager, I believe. It basically is used by ransomware in order to do just that. So if there are any handles open to files that it wants to encrypt, then it tries to enumerate them using the restart manager. And then if it is, then it will use this rm get list to get all the processes that have open handles to a given file. And then here they're just using they're acquiring or they're making sure that the current process ID isn't the one that has the open handle to that file, and then it'll open the process and then terminate it. So this is very similar to the functionality that we saw before, but this is using that restart manager interface, which is quite powerful. Let's see what else. Yeah, and that's it. So like not super complicated. Like the fact that it uses HC128 is pretty interesting, and then it uses ECC 25519 is also pretty interesting, but that's pretty common now. And then everything else is kind of straightforward. So let's look at some of the other functionality here. So we'll just call this write ransom node encrypt file. And this is again done within a thread. And then this thread is initialized for the number of, let's see, n count. Okay, so it's just the number of processors. So it'll basically create a whole bunch of threads, and then I just want to see where it's starting, because it should enumerate the drives. So I think this might be waiting in a queue. Let's see. Find first volume. And then, no, I think it's done in this too. So this is the one we already reversed, right? Oh no, it's a different one. Find first file. Find file data. Where's this? Am I crazy? Why is double clicking on this not showing me it? I'm too used to binge now. Okay, this is recursively enumerating these. Okay, so find encrypt file, and then this function is called where? Okay, calls find encrypt file, and then let's check out these other ones. So this is going to be we probably want to go from the start function again, just so we don't miss stuff, because we're kind of jumping ahead to the network stuff, but let's go through these anyways real quick. Yeah, so we'll go back up here and then thread. I know that's technically the function that's being called within the thread, but okay, so then once we have shares or paths that are passed as arguments, then again, it creates an array of those. And then this is also very common. They use this function called netShare enum to enumerate given network shares. And then they will acquire the total number of entries read, and then the total number of entries, and then this resume handle. And then they'll effectively enumerate given network shares for these SMB paths or server message block protocol paths. And then let's see. And then basically they're just enumerating each provided path for encryption in this function. So pretty straightforward. Okay, and then here they are looking for actual drive names, and then they'll use get drive type W, which will acquire the type of drive being enumerated. And then this just returns the type of drive. So this will be DW drive type, and then this will be checking for CD-ROM. Basically, it doesn't want to try and enumerate drives that it can't encrypt files on. And then if it's a remote drive, meaning that is a network share drive or is an SMB share drive, then it'll use this path to acquire connections to it. And then I just want to double check what get connection W does, but effectively that's what it's doing. So we have the local name, which is the pointer to the constant null terminated string that specifies the name of the local device to get the network name for. And then this receives the remote name. So yeah, it's basically just getting the name. I don't know why this is a pointer +4, but that's okay. And then this is provided here. Okay, so basically just ensures that the drive type is a network share drive and then encrypts it. And then let's see here, what else do we have? And is this just checking for more arguments? So I don't know why it's creating the mutex version 4.0, but it looks like it's using that to enumerate attached network shares and then encrypt those as well. So we can like doubly confirm what I just said by checking this call to wnet open enumW. And this will basically be the function that starts an enumeration of network resources or existing connections. So the scope is going to be important here. So let's mark that. So this would be resource. Should come up. Oh, weird. Maybe I don't have these types in IDA, but I think it's one of these. Let me just double check. Let's see if Gemini can answer. Oh, no, it didn't. I assume it is going to be resource connected, or no, resource remembered. So let's just say, let's create a new enum, and we'll do types, local types, add type. I will say con type, and then resource remembered. It was 2, right? Sorry, not semicolon. Okay, resource remembered, and then the wnet open enum. So basically that'll just look for any of the resources that are remembered on the system. So any network drives that are within the connection history, I believe. And then we want the DW type as well. So in this instance, it's going to be the third argument, DW type, and then DW usage. So 0 is probably going to be resource type any, but again, I don't think we have this. We don't really have to add all these enums manually because this is getting kind of boring. And then resource usage all is probably what it's enumerating. And then basically it returns a net resource pointer, which is then enumerated here using wnet enum resource W. And then each of the enumerated resources are passed to this function recursively. If the DW usage, this is going to be a net resource structure. And if the, DW type, what was it? Sorry, DW usage. Let's see, usage. Again, I don't think these are going to be an IDA, but let's see what this corresponds to. Sometimes these random docs have enum mappings. I should really get the, like wine. Wine should have them for sure. Checking for 2. So if it's a container. So basically if it's a container, then it continues to checks resource container. Then it basically continues to enumerate these recursively. And then if it is not a container, then it gets the remote name and then passes that to our file encryption function. Oh, and this is where get logical drives is being called. So this is what I was looking for earlier. So here, basically it's just enumerating all drive letters from A to Z using get logical drives. And then it's also using this sub 404 4T0 function. It sets up all the drive letters manually, which is funny. It gets the drive type, it checks if it's 1. If that's it, drive no root dir. Let me check get drive type. Yeah, that's it, no root dir. The root path is invalid. So it's just basically making sure that it's not invalid. OPC mount points. Okay, so if it's, yeah, so basically if it can't get the drive type, then it tries to mount it using set volume mount point, which is kind of interesting. So try to enum drive type mount invalid, something like that. And then let's see what else. Yeah, I think that's kind of it. Anybody have any questions? What do y'all think? Should we do some other stuff with this malware sample? Should we could see if we could write some Yara rules to identify this particular variant, or maybe give some thought. And I'm just going to hey, bad code. No, I didn't have to unpack this one. I actually can't remember where CyberJerry got this. Run it. Also, Yara sounds fun. Okay, yeah, I'll do that. But yeah, I'm just gonna run to the washroom. Again, I am able to do these streams for free and do all this content, put it on YouTube, whatever, because I run this malware analysis training and other services company related to malware analysis called Invoke RE. So I'm just gonna throw that in chat. I'm just gonna play a commercial for our malware analysis training. I know there's a bunch of people in the chat who already have the training, but I'll throw that up and then I'm gonna run to the washroom and then we'll do some Yara stuff. So I'll play that and be right back. Hey everyone, my name is Joshua Reynolds and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective Yara rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. Okay, so while I was off screen, I also logged in to Unpack Me, so we can use their Yara stuff because it's really good. Yeah, and we could probably also dynamically analyze this. It would probably be cool for some of the newer folks or even some of the non-newer folks to see the ransomware executing, and we can kind of confirm our dynamic analysis, our static analysis assumptions. So that may be cool too. So, okay, so let's go back to the sample in IDA. And let's see here, what do we got? So usually you want to write Yara rules based on the core functionality of the malware, and you want to make it functionality that's harder to change. So because of this, we could probably use some of the HC128 code in combination with some of the malicious attributes that they're using here. If we wanted to identify this particular version, we could look for this V4 string, for example. We could also pop quiz, what else would you all include in this Yara rule in this particular sample if you've been hanging out for this long? We could include the VSS admin string, but again, this is like pretty easily manipulated or changed. We could include the process termination strings, again, easily manipulated or changed, so not super dependable, but if this is a fork of Babuk that a lot of people are using, then it could probably be pretty good to use some of these at least. Let's see what else. Same with the terminate services stuff. Again, not super crazy, but so let's look at some of the HC 128 stuff. I am interested in what that kappa rule looks like. So kappa, whoa, this completely changed. What is this interface? Okay, so they're looking for these like rotation. So I don't know if all the byte representations of these, but I could probably look for these patterns in the stuff that we looked at. Because if they're using the HC 128 algorithm, they're probably not going to be able to change the library code all that much without breaking the functionality. So this is probably good instructions to signature on. So if I go to like the cipher code, let's see the generate key stream. Like this is crazy. But again, probably get a sig on. So another thing I'll usually do in IDA is set the byte code so that it's actually shown. So you can change the number of opcode bytes to 8. These are hard to see right now because of the, here, let me turn off the synchronization. But these are going to be the opcodes that we want to sig on that are made up of these byte sequences. So we can do shift right 16 followed by a move of 4 multiplied by D. And then usually you want to, like, let's say we capture these bytes. Usually you want to wildcard out the bytes that are register dependent. So that can be actually pretty hard to know off the cuff just because of how the opcodes are constructed. But here we can see like, okay, this is going to be a shift right with ECX. So ECX is probably E9 here. And then 16 is going to be the number of rotations. So we could probably safely get away with guessing in some instances. But yeah, so let's start with some of these shift operations because they're quite unique, at least at first glance. And let me get the VS Code instance. Okay, so let's do Yara, and we'll do rule, Babuk. What did we say the variant was earlier? Let's just say invoke Babuk, and then we'll have, we want strings, and then condition. And then usually you want these to be spaced, is the correct format, but isn't necessarily required for it to match. So this will be made up of the sequence, and usually I just copy like the disassembly so it's easier like this in the comments. Okay, and then again, let's wildcard these out. This is kind of annoying not having a second screen, but that's okay. So we'll keep the BA04, and then so we'll get rid of the E9. And again, like these opcodes are made up of those, so I don't know how much of this we want to get rid of. But the I multiplication is probably the 6B, so we'll get rid of C2 and E9. How about that? So I'm just going to wildcard these out. And there's other really good projects that'll do this for you, but like Benlex, but we don't have to worry about those today. In Binja, there's like copy as Yara, which is a cool plugin. Oh, IDA SigMaker. And then what's the best way to copy the opcodes in IDA? Yeah, so yeah, I was just talking about that lopsec. That's funny. Yeah, copy as Yara is really good. So I'll pull that up, but this is for Binja. I just kind of want to show it manually so you guys can understand my logic and thinking process. But yeah, shout out to Alden for making this. Basically, it'll do what I was just describing. So it'll wildcard out stuff based on the opcodes. So cool stuff. And then let's check out what Tumpus said. So IDA SigMaker, looks like there's a couple. IDA 9 and up compatible. I'm curious what they're using for the, oh, this is C++, cool. Okay, I don't really want to compile this. Is the other one Python? No, these are both C++, okay. So yeah, maybe I'll get that set up in this IDA instance or on my Linux VM, because that'll be a lot better. But yeah, let's try some of these artisan handcrafted Yara signatures. So again, same thing here. We could probably look for the shift lefts. These offsets, you don't really want to use these, like, I guess they're hard-coded relative offsets, so they might be okay. Parsing maker. Ooh, nice, man. Are there any dependencies? Nice. Okay, I'm gonna add this to the notes. So let's do, I just wanted to see what the code looked like. Nice. Open clipboard. Okay, I think I have to run this on Windows. Are you running this on Windows, Tempest? Because it looks like it's doing Windows calls from the Python. Or is that just for the clipboard stuff? I just want to know how it understands what it needs to wildcard. Add bytes, regex. Using regex for this? This is a giant Python file, so let's see. Example output, signature make form, set wildcard operand bit mask. Oh, cool. It's using the IDC for it. That actually makes a lot of sense. But yeah, I think this might not work on my Mac OS version of IDA. But yeah, let's continue with, this says it works on all platforms. Okay. But yeah, let's see if we can do one by hand, and then maybe I'll make use of this to wildcard everything quickly. Just make it a little bit more interactive. And then we can go from there. How about that? So, okay, so these various offsets look okay. So like the 16 shift, like all of this stuff should be pretty unique. This is kind of painful going back and forth. But yeah, this is very similar. So we could probably do a few of these shifts. And then let's grab some of the, like this one too. It's good. And then we'll try some other stuff. We could do a range too. So we could do more advanced Yara stuff with this sig specifically. C1. So this is C1 because it's shift rate ECX. And then so this is just going to be the HC128 encryption operation stuff. Usually I would add the rest of the disassembly that this corresponds to, but we don't really have to worry about that. So let's just call this HC128.1 for clarity. And then let's look at the core crypto stuff. So like this is where, I can't remember who was mentioning it earlier, who was asking about the imports, but like this is where you could sig stuff, is based on the import contents themselves, which could be an okay way to go. Let's see here. Oh, and I think this is is this the key? Okay, I just want to see if this corresponds to a known checksum algorithm. Oh, it's CRC32. So let me fix that, which is really common. So we could like even include some of these CRC32 checksum bytes. Again, a little bit harder to change, right? So if I hit Control E, that's kind of what I keep doing, and I should have mentioned that earlier, but let's include some of these bytes from the CRC32 algorithm in the file. A little bit harder to change. So I'll just say like, okay. And then what's the next thing we want? That might be enough, because like how many applications are going to be using HC128 with CRC32 that aren't this ransomware variant? I don't know. But let's give that a try. So let's copy this, and we need to set a condition. So let's just say all of them for now, and do that. And then unpack me. Hopefully my session is still active. Yeah, it is. So yeah, what's super cool about Unpack Me is they have this Yara editor and search interface. I think you can get this for free. But basically it'll search back through, I can't remember what the max is. I think it'll show us when I'm doing this, but I'm just going to copy this rule, and I can hit validate. There's that validate. And hopefully I didn't screw anything up. But basically it'll validate that the rule works, and then that it's not inefficient, I believe, because I think usually they don't want to run rules that will basically like just clobber their Yara engine. I don't know why this validation is taking a while. Save. I have to validate it before I can hunt with it. But basically, this is like a Yara hunt interface, and this will go through. So if I go to history, oh, this is me. These are my samples that I've submitted. That's why. This is like super old. I was testing, actually talking about assembly line. I created an assembly line plugin for Unpack Me like back in the day. So that's what I was doing there, and then doing some other stuff on the stream here. I should probably use unpack me more. Malware trends, live feed. This is what I was looking for. So yeah, this is like stuff that they're unpacking. I don't think it's real time. It's probably delayed a while, but like this is a sample that was just submitted, launcher that was downloaded from this website. It looks kind of sketchy. But yeah, so that's what is going to be searched for in this hunt interface. Why did I fail? Rule validation failed. I don't really think this is very complex. Let's try something like this. Okay, that passed. Let's try this again. Maybe it was just like a one-off. Or maybe I can just make my rule suck less. Maybe let's do something like this. But I don't want to make it too generic because then it'll match on a bunch of stuff. Okay, so that validated. Save, hunt. Okay, so then we can set like a bunch of parameters. So we don't want to really like search across scripts, for example, but we do want to search across the submissions, both packed and unpacked, and then the unlabeled ones too. So let's do that. And then Yara X is just the Rust version of Yara. So I'm going to hit launch, and then we might get a ton of hits, but we'll see what happens. Hopefully that CRC32 constant means that we don't. There might also be a ton of Babuk samples. Okay, 42. So that's a good number. So suspicious, exe. So there's some good functionality. Let's see, analysis report. So there is some unlabeled stuff in here, which is pretty cool. But which means our YARSIG might be better than some of the. I think I can share the community one, or I think I can share it with the community on Unpack Me. But if I go to one of these analysis reports, okay, Astrolocker. Why isn't it showing that? Am I crazy? But yeah, so what I mentioned earlier is it'll do a 12-week look back. So basically, it doesn't do like every single sample they have in their repository, but 12 weeks is really good. So let's see if we have. Okay, so there's these labels, but it's kind of weird because when I go, maybe it's just not showing the Malpedia ones. But yeah, that looks like a pretty good SIG. Does anybody have any questions for like why you would do this or what I'm doing? Or does this make more sense? Basically, we just want to find more samples of this malware variant to see if we can analyze them. Let's see, can I pivot to, they have this pivot interface thing. Okay, so it shows the packer. Indicator, generic ransomware. Okay, so I wonder how they're generating those indicator things. But yeah, if I go to any of these analysis reports, then I think most of them are going to hit that Astrolocker signature that I mentioned earlier that hit in my assembly line instance. Yeah, so I think probably what we can do next is we can take a look at this thing just encrypting my VM, and then we can step through some of the functionality, and then we'll call it. How does that sound? Any comments, questions, concerns? Okay, so I'll pull up my Windows VM, and I'm just going to restore the snapshot. Actually, I think it's an OK state. Hey, let me share that on Unpack Me so other people can take a look at it. Shared. Revision 2. Cool. And if I go to this link, it just goes to it. Cool. Nice. So if anybody wants that, here you go. In chat. You'll have to register for Unpack Me, but I don't think it's too difficult. Okay, so let's log into this VM. I'm just going to copy this sample over. Terminate for a bit, but I see this is still going. Where are you at now? So Permanel, I just wrote a Yara signature for this and then ran it on Unpack Me. So basically I'll show you the SIG. So basically, since the ransomware uses this HC128, I just took some shift sequences from that because those are harder for the ransomware to change between versions. And then they're also using CRC32 for checksum stuff for checking the checksum of a given file when they decrypt it. And they're using that for the key as well, I believe. So yeah, I just added some of those bytes as well to the Yara rule. And then I ran it against, let's see if I can go to the hunt history. So yeah, then it just matched against like 42 different files. So it's a pretty good number. And then I was just going through some of the results. So that's basically it. So basically you would do this if you wanted to find more versions or more malware samples associated with this malware family. And then if you wanted to do further research on what they're being used for, et cetera, et cetera. Okay, so let's go back to the VM. just going to copy this over. And then now I'm just going to run it dynamically to show you all what it looks like. Yeah, no problem. But yeah, I thought we could run it dynamically in a VM just to like confirm our static analysis assumptions. And it might be interesting for folks who haven't done a ton of malware analysis. Okay, so I have the share now. Are you running under X32 debug? Yeah, I'll be running it under the X32 debugger. Exactly. Oh yeah, this was the weird name. Babuk Destroyer Alex. I don't know if they just like append that to stuff in on triage, but okay, so rename this, and then it is an exe, right? Pretty sure I checked that, but let's double confirm. So usually, like if you have a malware sample executable, you'll use something like detect it easy to just confirm like basic assumptions about the portable executable. So in this instance, we can see like, okay, there's all these different attributes, including the fact that it is a well, that is 32-bit, 32-bit executable, that it has, where is it? Deal characteristics. Yeah, Windows GUI. So this is the Windows GUI subsystem. So this indicates that it's an executable. Okay. And there's other indications like its lack of exports and stuff. No, it's not a DLL. I was just double checking that it wasn't. Oh yeah, sorry. This is a different piece of malware. Out.dll. That's that I was using here. I should have restored a different snapshot, but that's okay. Okay, so now what you doubly want to make sure is that when you have a piece of ransomware running in a VM, you want to make sure that there's no shares attached to the VM because they could be encrypted. And then you will also want to make sure that there's no network connectivity. So I just have it host only right now with my VMware Fusion installation. And then what I'm going to do here is synchronize my IDA database with this, and then I'm going to take a snapshot just so we can restore it if we encrypt our files. Okay, so I'm just taking a snapshot, and then I'm going to copy this base address. So I'm going to right click on this address, go to follow in memory map, then copy this 11,000 address, or sorry, this 10,000 address. And then I'm just going to synchronize my IDB. So I'll go to edit, segments, rebase, and this just sets the program at the same virtual address as my debug session. I can hit F5 again to get the decompiler back up. And then should we take a look at the encryption functionality? I think that makes probably the most sense. Or we can look at the process termination functionality as well, live. So if I go to the windows are annoying. So for example, we could set a breakpoint on this address before it's going to terminate the processes. And then let's open up a process that it's going to target. So like Notepad it was looking for. And then let's make this smaller. And then if I go to that address and set a breakpoint, basically this will stop the execution of the program at the beginning of that process termination functionality. And then if I make this bigger, then we'll see, wait, is that snapshot done? Yeah. So we hit this breakpoint, it creates that snapshot of all the processes. And then basically this is going to enumerate all of those processes and then compare them against our list. So this is actually going to be quite lengthy just because it's going to compare them, every single process name to every single name within that list that we saw earlier. But I'm just going to set a breakpoint on terminate process. And if we take a look at what process is going to be terminated, this is actually going to be in that structure. So I don't know if it's going to be ECX. Is this a terminate process again? Exit code. All right, sorry. That's just going to be the handle. So I think we can look up the handle in the debugger. So if we go to, oh no, that'll be global handles. Can I look that up? No, it'll be here. Refresh. Let's see, will it show me the process handles? Doesn't really matter because I'm pretty sure it's going to be one of the applications I've opened. Yeah, okay. So see, what's kind of cool in x64 debug is that you can map the handle value, so to A0 here, to this handles tab, and then we can see that this corresponds to a process, and then that this is for notepad.exe. You ever use anything like Cape or AnyRun for behavioral analysis, or have any proprietary hypervisor stuff you're running against? So actually, I was showing a triage hatching triage run earlier for this sample. But yeah, I'll use Cape usually internally, just because it's the best open source sandbox, in my opinion. Do you use any sandboxes? Okay, yeah, so basically not super crazy, but if I jump over this terminate process, then Notepad closes. So, wow. But kind of cool. And then say we want to look at the encryption functionality. I can actively look at the HC 128, this stuff, because this will actually encrypt file bytes. What might you miss with something like Cape? That you get visibility into debugging, I assume behavior outside of this API calls mostly. Yeah, exactly. So like, I think Cape would do really well for this type of malware just because it's like pretty simple. But when there's a lot of obfuscation and like process injection and stuff, then it becomes a lot harder. So like, yeah, basically what you said is the surrounding functionality of the API calls. Because just because a certain API call is called doesn't necessarily mean that a certain piece of functionality is being executed or is not executed. So, for example, in this file operation, but you could infer this using other stuff in Cape, but for this file operation, it's basically from the Windows API standpoint, it would look like it's just reading and writing data. But since this is not in fact using any of the Windows APIs and is using this statically linked HC128 stream cipher, Cape wouldn't necessarily know that this is actually encrypting file data unless there's probably heuristics in the sandbox to know that, okay, if I see a whole bunch of sequential writes of files, then it's probably ransomware. Is any public samples try to evade Cape hooks? Yeah, totally. We took a look at one on stream a few months ago. It was BRC4, like that C2 framework. So they use direct syscalls. And then a lot of the time they'll like reload the dependency into memory to overwrite any user-lined hooks that like Cape might have, etc. Hopefully that makes sense. Okay, so yeah, we can do like, I assume some of that is just coincidentally impacts Cape. Yeah, exactly. That's exactly right, Perminal. A lot of stuff has hooks, including AV and EDR and whatever that they're trying to evade. Okay, so let's watch this encrypt some file data for fun. So because it's asynchronous, as in like there's threading, this is probably not going to be super intriguing because it's going to be like random pieces of file data that's encrypted, but let's try it. Like it's not going to encrypt each file sequentially because it's using threading. Wait, crap. Let me restore that snapshot. So this is why it's good to have snapshots with ransomware, because we don't have to worry about anything that might have been encrypted already. Okay, so let's get that address again. And the reason I messed that up is because these aren't synced right now. So let's go there. And then here. Okay, so that's why it didn't work. Okay, so there should be, okay, so it's encrypting this Python file, this python.ico thing. And if we look at what parameter was the file data, LP buffer. So the third parameter, so if we look at the stack, then that's going to be follow. If we look at the stack, then that's going to be this. This is another pointer. It's a stack address. Okay, so that might be, is this doing read file? No. Generate stream. All right, let's continue. Okay, now it's encrypting this Python CHM file, this Python DLLs file. So if we like copy one of these paths, I just want to go to this. These are pointers. So, not as straightforward to get the data as I thought it was going to be, but that's okay. So if we go to like this directory, for example, where this path is, so I'm just going to copy that out of this buffer here, and then the DLLs directory is what we're in, yep. So py.ico. So we can see like a lot of these are already encrypted. So if I go to py.ico and then open it in a hex editor, it's currently opened by our ransomware process, so I can't open it. But you would see this as being plain text, and then it'll be encrypted afterwards. So like if I open any of these guys that were just encrypted already, then we can see this whole file was encrypted. So I can go back now. I don't know, I won't worry about that. Okay, so yeah, that's kind of like the gist of it. Basically, it's going to iterate through the entire file system and encrypt all these files. So if I just keep hitting run here, we can see it encrypting all of these different files with this stream cipher. And then presumably the key that it's encrypting with the elliptic curve cryptography is being appended to the file as well. So if I go to, like we could reverse the encryption footer. Maybe we can save that for another stream. What do y'all think? How's everybody doing? Winding down? Anybody have any questions? And it should also be writing the ransom note to that directory. So here's the ransom note. Cool. Well, we could probably wrap up there for this week. Kind of just have your stream in the background, so I'm not 100% sure following along, but I thought based on a prior comment, this was Rust. Oh yeah, no. This is actually C, and then the Rust and Golang stuff I was talking about earlier was just a question I had in chat about whether or not the person should learn to write Rust or Golang in order to be able to reverse engineer it effectively. So that's all that was. But the Python stuff was just these are just the files that are being encrypted by the ransomware, but the ransomware itself is written in C, which is this code here. Yeah, thanks everybody for sticking around. Appreciate you hanging out for the stream. Come hang out in the Discord. Again, if you want to check out our training stuff, you can go here. I won't play that ad again, but if you want to learn how to do all the stuff we were doing today with IDA or Binary Ninja, definitely check out our training. And then let's find somebody to raid to pay it forward. I'll upload all these notes, and if you hop in the Discord too, we have a malware analysis study group where we were looking at this particular sample, which is pretty cool. So if you're interested in continuing to work on this sample, it looks like Fixit42 is streaming, so we can raid Fixit42 since they raid us often. I don't know where they are, but the chair is empty currently. But yeah, I'll see if we could raid them. How many viewers? They have 3 viewers. Maybe they're not on right now. Hack the Box Danny. Thanks, Lopsec. Appreciate it. Thanks, Bad Code, for hanging out. Appreciate it. Let's see if there's anybody else. Cool. Last time I was in software and game development, I forwarded you all to a person speaking Portuguese, so let's not do that. Let's see here. Automated. Leaking next Ludwig event. Okay, not that. Just Cavino. Okay, let's raid this person. Is it? Which one? This one? The greatest clicker game to ever exist? Is that why it's clickbait? I don't know, just read the title. Okay, cool. Alright, let's raid this person. Alright, thanks y'all for hanging out. Really appreciate it. Hopefully I'll see you on Discord or any of our other socials, but yeah, have a good one. I'm going to kill the stream once I hit raid now, but hope you all have a great weekend, and I'll see y'all next week. Take care.